do now, I actually want to pull us back to our exit ticket from the other day. And I know not everybody was here, so we're going to talk about this one together. We had a lot of people out sick. So what our exit ticket was on a practical level, thinking about real world applications. It's important to realize that a cleaner that we're going to use on a metal surface contains sulfuric acid. And I've got two really good reasons why we want to be aware of the reaction between an acid and a metal. And you guys told me that the reaction of an acid and a metal is going to make a salt and hydrogen gas. So could I have somebody either type for everybody to see in the chat or to unmute yourself? Tell me one of the reasons why it would be a good thing to not use an acid while cleaning a metal.
Certain acids can react extremely poorly with metals and release really toxic gases into the air. I know with the sulfuric acid example, what can happen is if it touches like aluminum or certain types of metal, it just releases pure hydrogen gas, which is a really bad situation.
Yes, yes, absolutely. Can anybody explain a little further why that hydrogen gas is going to be so dangerous? And I'm seeing lots of corrosive things. That's exactly. Oh, sorry, go ahead.
Oh, no, it's okay. Like hydrogen gas is really flammable as well.
Yeah, super duper flammable. You've got it perfect. So yeah, Olivia, thank you. We're going to be producing that dangerous gas. It's going to be mostly hydrogen because it's going to be exothermic. Maybe some of the sulfuric acid even turns into a gas, or there's particles of it going around. Like, so right. That's also dangerous. And Fiona's absolutely right. That hydrogen gas is going to be flammable. So even a minor spark or even a warm room could be enough to set it off. And so true, we've got Faduma and Fiona both talking about the corrosiveness of it. So it's going to like eat through the metal in that process. And so we'd be ruining whatever product we had. Just because we can't do it in school right now, oops, I wanted to show a super fast video. Exit that, exit. And I'm just going to show the very, very last part of this. So this person was taking magnesium and an acid, reacting it, bubbling the gas into a solution that contained some soap and water so that it would bubble, and the bubbles are holding this hydrogen gas right now. And so he's just collected a little bit of hydrogen gas, and this is what happens. Okay, that went so fast. Did you guys even see it catch on fire? It went really fast. Let's go back a little bit. Oop, oop, nope, I don't want that one. Go back, go back. Go back. Okay. I will send it to you guys instead so you can see the whole thing, see how he makes it and all of that good stuff. So it is really, really fast, which is really not a good thing if you are using it as a cleaning substance. So note to self, be cautious about the cleaning chemicals that you use and on what surfaces. Okay, where'd my PowerPoint go? Boop, boop, boop. There we are. Present this again. So back to the question, and we'll go through that quick, and then you guys can stay on and ask me questions if you need to. I am loving that so many of you remember what products are formed in this type of reaction. We've got a carbonate, and so we know from a carbonate reaction that there's going to be 3 products, and we can deduce them pretty quickly. So again, our goal is to review some of last year's stuff overall. So in doing that, let's look at the charges of stuff. We already talked through on Tuesday about sulfuric acid, so we won't go through that one again. SO4. Can you guys remind me, is that solid, liquid, gas, or aqueous?
Aqueous.
Yeah, aqueous. Thank you. Aqueous. Beautiful. So we've got H2SO4, which is aqueous, and we are reacting it with potassium carbonate. So we need to think of charges again. So another name for that is oxidation number. We need to know the oxidation numbers of these things. One of our rules for oxidation numbers is that everything in the first column on the periodic table has the same oxidation number. And potassium's in the first column. So type into the chat, what is the charge of potassium, aka the oxidation number? Nice. Awesome. Perfect. So potassium is K1 plus, and we said that it's with carbonate, CO3, and this, I'm seeing a lot of you have figured it out already, is a 2 negative. And so to get an oxidation number overall equal to 0 when we put this together as a compound, we get exactly what I'm seeing on so many of these, K2CO3. Because if CO3 is a -2 and my K is a +1 and I have to be 0 overall, I would multiply this by 2 to get to that 0. Good. So we've got K2CO3. It could either be aqueous or it could be a solid. Since we don't know, I'm just going to say it's solid. It's probably in a powder form, most likely, if we're doing this reaction in the lab. We probably haven't dissolved it in water. That would add another variable onto our reaction. So what happens? The cations exchange just like they did the other day. So cation, cation, the cations exchange. And if you missed the Tuesday class, because again, I know a lot of people were out sick. If you missed it, check the video because we went through a bunch of things that I'm referring to, but not actually talking about right now. So those two switch places. So we would think that we would have a salt with the potassium, which we said is a 1, and the sulfate, which we said on Tuesday was a -2. So we have K2SO4, which again is going to be aqueous because it's a soluble thing and there's going to be water in there, just like we talked about on Tuesday. So we've got K2SO4. And if this was a normal double displacement reaction, which it looks like it's going to be, then we would say, okay, well, we have some H1 pluses and some CO3 2 negatives. So we must, as a result, have H2CO3 aqueous. That seems legit, right? It seems like it could just be a double displacement reaction. But I see some of you shaking your head, no, you're right. We know, because we've been studying this over the last year, that this H2CO3 actually decomposes. So rather than a double displacement reaction, we would probably consider this a decomposition reaction overall. And I saw so many of you right off the bat said that we're going to form CO2 and H2O. Because you remembered that from last year. That's excellent. So we've got CO2, which, what state is that at room temperature? Solid, liquid, gas, aqueous. Yeah, gas. And H2O. What state is H2O at room temperature? Yeah, it's a liquid. Good. So I'm going to cross off this H2CO3 because it decomposed further. So I'm really forming this K2SO4, CO2, and H2O. Good, good, good. So now all I have to do is balance it. again, we can do like we did on Tuesday. You don't have to write out the whole thing. What you could do is do like the number and then the dots to represent each one in order, because we know that we've got them all written in the same order right now. So once you know the answer, go ahead and type it in. I'm going to double check that I got everybody right here on attendance. Awesome, awesome, awesome. Awesome, and I see it there. You guys have told me it's already balanced. Already balanced. So I tell the IB examiner that so that they remember or they know that, yeah, I did actually look to make sure it was balanced. I didn't just give the products.